We'll start the second lecture of the morning session. This is by Sumilan Bannerjee. He'll talk about SYK models.
Thank you. Yeah, so I discussed last two lectures essentially some basics of SYK model. So starting with the motivation in the condensed matter physics, which came from this non-Fermi liquids and all. But then when we went into this model just sort of as an interesting model, and I tried to sort of derive very basic things about the saddle points, the G sigma actions, and some of the properties of the low energy fluctuations. So today lecture, I'll be talking about some large-end calculations of entanglement and non-equilibrium dynamics in this SYK model. So I'll see how much I can go up to this thermalization, but I'll try to certainly discuss the calculation of entanglement in the large-end theory in the SYK model. Okay, so first part of this. So yeah, so I was a bit lazy, unfortunately, and I didn't prepare a handwritten note, but I'll be happy to go over the board, and I'll try to also give some notes. As Spenta also asked me of these lectures and also these presentations. Okay, so let me. So first part of this, I'll try to discuss a very general method of calculating entanglement entropy in quantum interacting system. Many body system. It's a general method, so it's not specifically limited to non-interacting systems or SYK model or as such. So it is kind of a equivalent to this type of replica, Cardi-Calabresi type of replica method. So you can sort of use it in a similar way. There are some advantages, at least in my opinion, if you are applying this to models like standard quantum many-body models like Hubbard models and other things. So I'll try to emphasize that point. So the first part will be some general discussion of a method for calculating entanglement in interacting system. Okay, so so these are sort of mainly from this reference over here, and then there are some related reference on the quench in SYK model. So I must say I will not be able to do reviews of this field much. I have just tried to put all the I mean not all. As few of the references, the many of the works that have been done on this kind of topics in SYK model, there are many works by people even here, and you should look at this. Unfortunately, I will not be able to review these works today. Okay, so let's just start from the very basic things, which is about entanglement, as we all know. So, so generally, I'm thinking about pure state entanglement at this stage. Of course, the method that I'm going to discuss also you can extend to mixed state entanglement like entanglement negativity, but I'll not discuss about that. So for the pure state entanglement, the standard process is of course as well known that you take a system in a pure state and then you look into some reduced density matrix of a subsystem, which is obtained by tracing over the rest of the system, which is the standard formula, and then you calculate some entanglement measures. The most preferable one, of course, if you could calculate, which is the von Neumann entanglement entropy, which is given by this. But the kind of calculations that I'm going to discuss, this type of field theory, many body calculation, there you cannot directly calculate this. It's a similar problem like what I was discussing yesterday about using replicas, that you cannot directly calculate the replica limit. In that case, it was n going to 0. In this particular case, it will be n going to 1 limit. Okay. So what we use is this quantities which are this Renyi entropies, subsystem Renyi entropies, which you can calculate for some integer n, and then try to take the limit that n goes to 1, which gives you this von Neumann entropy. So that's the strategy that one follows in this type of calculations, and of course in CFTs and others there are beautiful formulas that one obtains which you can analytically continue to n going to 1, and you get the result for von Neumann entropy. So the method that I'm going to use for SYK model, this we have not been able to do yet. But of course, you can calculate all the other Renyi entropies in this method. Here also you yes. Yeah. Oh, right. So that replica is there for SYK model. There will be a disorder replica. So that I will come to. Okay. So you have to take both the replicas in this case. So this is I am just right now talking about let's say a given realization of disorder. Okay. So. Okay, so now one question is, of course, we have heard talks here that why it is important to understand entanglement in relation to quantum gravity. So you can also ask that, I mean, why people are interested in entanglement in condensed matter physics. So let me just sort of give a very brief few points on that. So it turns out that, again, just like in the quantum gravity, I mean, in condensed matter also you can try to characterize phases using phases and phase transitions, etc., using these quantum correlations, these intrinsic quantum correlations, which is captured partly by this kind of entanglement entropies. So for example, it is as well known in all of physics that the standard result is that if you have a, and in the context of condensed matter, it translates to that if you have a gap system, typically in higher dimension, I mean typically any dimension, so you get this area law. Okay, so the leading entanglement entropy, where L is the size of the subsystem, it goes like L to the power d minus 1, and then there are some corrections. Now, these corrections also turns out to be very important in many cases, and certainly in condensed matter, because in topologically ordered system, these corrections essentially gives you a window into topologically ordered phases. So if you have some corrections like this, which is universal, then it tells you about the topological order. At least there is a topological order in the system. Okay, so that kind of thing is important to characterizing models like toric code and Kitaev honeycomb models. Yeah, that's the same results. I mean, there is no, yeah. I mean, right. So that Hastings results, and I think the calculations, whatever case by case basis you can do, right? I don't think there is. Yeah.
I mean, this is of course for ground state.
Right. Yes.
So as long as you have local Hamiltonian.
Yes. Right. Yeah. Yeah. Okay, so for gapless systems, so if you have, let's say, one dimension, one spatial dimension, 1 plus 1D, then for gapless bosonic or fermionic systems, it is well known that you will get a logarithmic universal violation of this area law. You will get a log L whose coefficient is universal, determined by the central charge. For example, if you take a Luttinger liquid or even free Fermi gas in one dimension, then you will get these two sort of CFT modes, chiral modes, and then that gives, if you put in this formula, it will be 2. If you have spin, then it will become 4. So that is the result for the gapless system, right? So you, in one dimension, you will get these violations, these universal violations of the area law. So no, one dimension, no area, it will be just a constant, L to the power d minus 1 d equal to 1, right? So that's very well known. So if you take standard spin chains which are away from any critical points, then you will see this, that the entanglement entropy doesn't grow with subsystem size. Okay, so this is in fact one of the characterization people use to characterize gap system in condensed matter. Okay, so now you can ask that, are there such violations in higher dimensions in this? And it turns out that free fermions in higher dimension, not gapless bosons, but if you have gapless fermions in higher dimensions, so for example free fermions, then you will get a logarithmic violations with the area law thing L to the power d minus 1. And if you have a free fermion like a Fermi gas or even Fermi liquid, then you can actually calculate the coefficients of this, which is known as Widom coefficients, which also you can calculate numerically, and also you can calculate for the free Fermi gas. It's essentially determined by this 1D. So effectively you have a Fermi surface, and at the Fermi surface you are sort of thinking about many decoupled 1D modes which are only going outward from the Fermi surface, and that gives you this counting of the prefactor here. No, not only for non-interacting fermions. Yes, no, not for interacting. No. So there are other examples where I mean there are some specific examples like wild fermions in magnetic field in higher dimensions and certain kind of non-Fermi liquid Bose metals, things like that. People have argued that they give this violation. Okay, but this is not very common in higher dimensions. So higher dimension typical gapless systems will give you area law, okay, for the ground state, unlike fermions like bosonic systems, spin systems. Okay, so now the another aspect, this is also interesting from the perspective of condensed matter, which is also you are trying to characterize the dynamical phases of matter. So One of the thing is about thermalization and absence of it, which is non-thermalization, for example, many-body localization. And one of the robust characterizations of these phases also comes from entanglement, okay, which is also again related to eigenstate thermalization. But one of the sort of simpler way to characterize it in numerics, for example, is through calculating entanglement entropy of eigenstates or time evolving states and try to demarcate phases, dynamical phases of matter, which is plotted here as a function of disorder and many body energy density. So you can actually have a many body mobility edge which demarcates between states which are ergodic and states which are interacting Anderson localized, which are called many body localized states, and you can distinguish them by looking into the same diagnostics, which is whether the entanglement entropy varies as L to the power d, which is called the volume law, or whether it varies like L to the power d minus 1. So this many body localized state, even at very high energies, extremely high energies, they have area law. So even though they are extremely high energies, they look like ground states. Okay, so that's sort of the characterizations of these unusual phases of many body localization. So this, of course, this problem turned out to be very complicated and unsolvable, and a lot of debates, and even whether many body localized phase exists or not, there are a lot of questions in recent years. But what it did is it actually led to this kind of paradigm in condensed matter where people started looking into what are known as entanglement transitions in different systems, simpler systems which are more related to the quantum computers, which are basically these unitary gates, systems with unitary gates interrupted by measurements. Okay, and here by tuning the strength of the unitary evolution and the measurement, you can actually tune transitions which are somewhat similar, entanglement transitions from volume law to area law. Okay, so this has led to completely new paradigms. These systems give interesting critical points, which is some interesting CFT type behaviors. So this has led to all this a lot of work on this field. Okay, basically characterizing things using entanglement. Yes, here at the many body localization transition. Yeah, so there are sort of controversy about this. These are all numerical results. So people used to believe that this is also volume law, okay, at the transition. Yeah, but that is only sort of a numerical result. So there is no method really which can access this line with any confidence.
So
okay.
There are any kind of subleading correction to the volume law, like while doing transition from the.
I mean, you don't even know the leading correction. Forget about the subleading corrections, right? So what is this critical phase is like a mystery. I mean, there is no method also, you know, even numerical method that can access this. Yeah, this is quite a generic phase diagram. So any systems, any generic system, if you have strong enough disorder, this you will see. Okay, local systems. Okay, so now the question is that how do we calculate entanglement of many body states? So I'll just list some methods which are quite often used in different areas, and some of them specifically in condensed matter system. So of course, for non-interacting systems, you can, as we know, that you can just diagonalize the non-interacting Hamiltonian, and then using, because only you need the 2-point correlator to characterize the full state. So you can everything you can calculate using this thing called a correlation matrix. Okay, so you can calculate the full entanglement spectrum, everything just using this non-interacting diagonalization, and using those eigenstates and eigenvalues, you can look into correlation matrix and you can calculate everything. Okay, for very large systems, relatively very large systems. Interacting system, however, these methods, numerical methods, become extremely sophisticated. Of course, you can do sort of less sophisticated brute force calculations like exact diagonalization, but that has limitation to small system. Other methods are like density matrix renormalization, DMRG, and my matrix product based approximations, and also you can do quantum Monte Carlo to calculate entanglement entropy. But all these methods have some problems because DMRG, for example, has particular ansatz for the wave functions, so that typically applies well for the one-dimensional system for ground states, and then quantum Monte Carlo you can only do in imaginary time, the Euclidean time, Euclidean, and as a result you can't get real-time informations, and also it's quite limited by the accuracy and other things. These methods. Yes. Mm-hmm. Yeah, so there are some works that people have done, but it's not controlled still. I mean, you really don't know how to control this calculation. Yes. Yeah. So of course we know that beautiful methods in field theory, which is which Matthew Edrick also was mentioning. I think maybe other people. So I am just drawing it slightly differently, but it is same thing. So essentially use this replica field theory, I think, which is initially popularized by Cardi and Calabresi and collaborators. So effectively what you have here is you have one system which you have separated into two subsystems, let's say, and here I have drawn a diagram for third Rayleigh entropy. What happens is that Matthew Edrick was drawing this Riemann surfaces, so essentially I am drawing it slightly differently. It's the same Riemann surfaces with some conical singularities here. And essentially you apply you have to apply a different kinds of boundary conditions. So this one has to take through 3 Riemann sheets. This one the B subsystem only remains in the single sheet, and then you can have T3 copies of this like that. So you can basically write the path integral in this kind of a manifold, and then you have to solve this path integral using some approximations, right? So that's the standard method. And this has been, of course, used with wonderful results in CFTs and other things, as we know. But if you are trying to apply this method for general systems, general many-body system where there is no such powerful methods like CFT, obviously, then it's become very difficult to use it, at least to even handle this type of method, at least for a person like me. So the question was that can you sort of simplify this method and simplify this boundary condition using some method, and that's what I'm going to discuss. So it turns out that this boundary condition is completely rigorously you can transfer into a different problem where you don't need this boundary condition. You apply the same boundary conditions on the fermion, but the price you pay that you have some extra source fields that takes care of these boundary conditions. Okay, and this is done completely mathematically rigorously using some identities which I'll show. Okay, so that's the idea. Before going into that, let me just mention again why this manifold sort of this Riemann surfaces come. So when you look into entanglement, so let's say you are trying to calculate right now, let's say just Rayleigh entropy. It's not entanglement entropy, it's just some mixed state. I'm just trying to calculate a subsystem Rayleigh entropy. Okay. Of course, you can ultimately try to take beta going to infinity limit, which will give you the ground state, pure state entanglement entropy, but this is how typically you do. So if you are writing this nth order Rayleigh entropy, then the trace formula will be something like that. So you have trace A, but then this trace B, trace B, trace B like that, right? So now you can immediately see if you are trying to write a path integral for this, then typically you will use some coherent state basis to write this. So the coherent state basis, the trace will connect this to N. So there will be some anti-periodic boundary condition for the A subsystem. However, the B subsystem, the boundary condition is different. It is anti-periodic inside, right? And that translates to this picture. Okay, so essentially, and you can do it for bosons also the same thing. It will be a periodic boundary condition, but that's basically how this thing comes. Okay. So you can of course do it, and all the results I am going to discuss you can equally calculate using this method. I mean, there is no problem, and people have done this. Some of the references I gave, you can look at them, and people have done calculations of entanglement entropy in SYK using these methods. Okay, so there is no problem using this method at all for SYK at least. Okay, so now I'm going to this yes.
So in the SYK is finally you get a replica saddle point.
Yes.
And then you do
yes,
it.
Yes. Yeah, I'll show the okay, so this method originally came from Chakraborty and Sen Sharma from TIFR. So they did it for the bosonic systems, and then we are inspired by their work. We are trying to generalize for the fermions, and independently they also generalized for fermions in this work. So we applied it for SYK model and Hubbard models and other things using some approximations. They used it for some other problems, but it's the same method. We arrived at the same kind of thing for the fermions. So let me just discuss this method. Again, I'm not going to discuss the full derivations of this, but it is kind of straightforward if you already know what to use. So the idea, so let me just tell you what is the idea, and this idea actually came from a work in quantum optics by Cahill and Glauber. So it turns out that let's say you have some operator O. So this operator, so I am now thinking about, of course, a system which has some fermionic degrees of freedom. So this operator O is a function of C dagger C. And this could be an operator which has local support in a given subsystem. It need not be operator of the full system. So some operator, let's say, which has only support in the A subsystem. So then, of course, this operator will be a function of the basic variables, which are the C dagger C, which are the things which are giving me the tensor product space. So then it turns out that you can prove that any operator can be expanded in the basis of what are known as fermionic displacement operator, which was introduced by Cahill and Glover. Okay, so this is exact identity that you can prove. So this exact identity was not there in Cahill and Glover. This is something that we found out, and also these people found out. Okay, so this makes the calculation possible. The identity that was there in Cahill and Glover, you couldn't easily write a path integral for that. Anyway, so that's sort of a technical point. But at the end, you can write any operator like this using this displacement operator. So if you wish, what I am doing, rather than in the standard replica method, rather than using the coherent state basis for the operators, I am now using this displacement operator basis. Okay, and of course I can still use coherent state later, but this is the idea, right? So it turns out you can calculate. So these are sort of the expansion coefficients. So you are expanding some operator in an operator basis. These are the coefficients. So now these objects that appears here, the zeta and eta, these are Grassmann numbers. Okay, so these are fermionic Grassmann numbers. And if you are doing a calculation for an operator in the A subsystem, then you will only have Grassmann numbers for the A subsystem. So this summation will go over the A subsystem only. Okay. So now you can see that a simplification happens. So you can now use this, take the operator as the reduced density matrix. Okay, so the reduced density matrix will be only function of this C dagger C in the A subsystem. So you can apply this identity, and then you can sort of multiply. So you can use the identity for one factor of rho A. So I am discussing for the second Rényi entropy, one factor of rho A, and then multiply with another rho A. Then you will find that the second Rényi entropy is related to this object. Okay, so it's just from this operator identity. I'm just using this. So now, so what do you really gain from here? So the thing that you gain is this. So now, if you see about this trace, so I have still these traces here, and this rho A is trace B rho. So that trace is still there. Okay, but you see that this trace, so this operator, this displacement operator that appears here is only acting on the A subsystem. Okay, so this trace B rho that you have here, so this trace B, you can actually take it out. Okay, so you can write this object at a total trace, where essentially you are calculating expectation value of the displacement operator in the A subsystem. So it is somewhat like this twist operators. I think it's basically same thing probably in the CFT, but it is done in sort of more operator way. Okay, here.
Not necessarily for CFT.
No, not necessarily for CFT. This is general. Yes. So that's the thing. So now once you write this, so now I don't need to deal with reduced density matrices. I just deal with the full density matrices. Okay, so then I can just write down the usual crank that I discussed. So for example, SYK model, the calculation I discussed, you can just try to do it for this now. Okay, the G sigma field theory for this. So you have to do two G sigma field theories, for one for here, one for here. These two theories will be coupled by this common Grassmann source field that they share. Okay, which is ultimately you have to integrate out. So this is a field theory where you cannot take at the end the source field to 0. So you have to keep it a finite source field, and in fact you have to integrate over the source field at the end. Okay, so that's sort of the theory that you have to deal with to do this. But the advantage, as I said, that because
you question. Yes. For what does this displacement operator look like for the bosonic system?
It's actually it looks like exactly same. You just replace with the bosonic operator here and complex numbers here.
Is this so? When we talk about coherent states, we have this displacement.
Yes, same operator.
Same operator.
Yeah, so these operators are also will generate the coherent states. So coherent states, the fermionic coherent states are eigenstates of this operator. So usually we do it for the bosonic case, right? So the bosonic displacement operator gives you the bosonic coherent state. So that same thing is true for the fermionic displacement operator.
So this is So this is like using the coherent state base.
Is exact? No, but the operator expansion I have still done using these operators, right? So I have not yet using coherent state basis. I have used operators which gives you coherent state. I mean, ultimately, which has a simple form in the coherent state, right? So that is important. Yeah. 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 Mm-hmm. Yes. 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 Right. You can get different combinations. Yes. Okay, so that's the thing. So you now write a field theory, and this field theory will have usual boundary condition. Okay, because you have this total trace. You never deal with this partial traces. So that's a very simple idea, and then rest is actually very simple. So what you do here, you write the so if you are dealing with thermal density matrix, then you just write this path integral. Only thing you are doing, you are calculating expectation value of this exponential operator. So you have to insert this operator at some time. Okay, now if you have to, of course, where you insert it doesn't really matter, but the thing is that once you insert it somewhere, it is like a gauge choice. So you choose a special time because you have to do the calculation with a finite source field which is inserted at some time, right? So then the problem is that this field theory now breaks this time translational invariance of the original problem. So you have to deal with a problematic field theory which breaks this time translation invariance. So this is the same price that you pay when you do this on the Riemann surface, right? Because there also you have to deal with this boundary condition. So it's you can't. That's what I'm saying is equivalent. It doesn't anything simpler or better in this way. Okay, so it's just replacing these things. Okay, anyway, so you can, so if you insert this in the field theory, you can write this as extra term in the action. So the standard action will be there, the standard action, the Lagrangian that you have will be there, and then you have this extra term which I am going to call the kick term, because they are essentially, if I write it in the continuum notation, so they look like a delta function kick that I am giving there, okay, because I am inserting at some point. The time that I am inserting it again is arbitrary, but yeah, but once I choose it, I choose it. So okay, so this also, there is nothing about thermal density matrix. You can just do it for any density matrices. Okay, so time dependent density matrix, even non-unitary evolution. So I've been using this kind of we have been using this kind of things for other problems of measurements, non-unitary dynamics and things like that, which I'm not going to discuss. But you can, I mean, this is a very simple method. You can generalize to essentially any formalism like Swinger-Keldysh formalisms or Lindblad formalism. You can do it. Okay, so there is no issue. And so first thing that you want to check that whether you can get the simple results which are known from the non-interacting fermions, and that you can get it very simply. So for non-interacting fermions, when you write this theory, so of course I have this action, this extra term. Now here I have an action S which will be now quadratic, because I have a non-interacting fermion, I have quadratic action. Okay, so then what I can do, everything is quadratic here, because this factor that I mentioned, yeah, so this factor is a quadratic factor. It's a Gaussian factor, which is involves the source field, and then I have these Gaussian fields, the Gaussian source field and the Gaussian dynamical fermionic variables C bar C. So I can just integrate them out, right? Because it's just Gaussian integral. So if you do this Gaussian integral, you can show almost immediately that you get the standard results using the correlation matrix. Okay, for the Renyi entropy, which is known from other ways of calculating, but this you can immediately get within few lines, right, using this method. So okay, of course, for the non-interacting system, there is nothing you are gaining from this method. So now the question is, how do you gain anything from the interacting case? How do you organize this? So one thing you can do, you can still try to do the same thing for the interacting case, which is you integrate out the fermions, the dynamical fermions, the C fermions. Then of course what you will do, because it's an interacting system, it will generate essentially a series it essentially generate a perturbation series in this Grassmann fields. You will just generate some effective action for the Grassmann fields, and that will not truncate because it will have the 2-point correlations, 4-point correlations and all that. Okay, so it will not truncate, and there is no small parameter here. Okay, when you do this, because this term is order 1. So but this Rajdeep and all they have used this method, so we are not directly using this type of methods. Okay. And now, so what I am going to do is mostly now related to this kind of large N models or some dynamical mean field theory. You can actually do slightly differently. So here what you do is you, instead of integrating out the fermionic, the dynamical fermions, you actually integrate out this source fields, okay, from that theory that I showed you. So this one, yeah, from this one, because everything is Gaussian at this level, so I can just integrate out these source fields, okay, because at the end I have to anyway integrate it out. So once you integrate this out, then it turns out that it adds a very simple term. I mean, at least simple looking term. Dealing with this term analytically may be still very difficult. So what it does, it actually just adds a self-energy term to the fermions. Okay, because if you integrate out this source fields, then the source fields is linearly coupled to the fermion. Right, so the source fields are linearly coupled to the fermions. So if you integrate out the source fields, then you get just a quadratic term for the fermion, and that looks like a self energy. Okay, so it's just the addition of a self energy. That's it. Okay, to the formalism. Of course, you have still the interacting term that you have to deal with, but you can now try to formulate an approximation scheme using this as your Bayer-Green's functions. Okay, of course, you have to deal with something which is time translationally non-invariant, meaning that this term now has these delta functions, which I am calling a delta function kick, and it also now couples these two replicas, these two traces that I had, it now couples this. So this method also has replicas. Of course, you are not getting away with replicas, right? And this thing you can generalize for nth order Renyi entropy. You have to just use this iteratively, this identity that I showed. Okay, you can generate the series for that. And this can also be used in quantum Monte Carlo. There are some discussions regarding that, but anyway. Okay, so now, to this, so this is sort of the general method I wanted to tell you. I mean, I'm going to apply this method to SYK model, which is at least to set up will be very straightforward. So one thing I should mention that beyond SYK model, there is an advantage of this method maybe compared to the standard replica method if you are away from CFT and all. Which is that you can actually have a nice interpretations of this kick term in terms of a non-equilibrium work. Okay, so this is how. So generally, I mean, if you are dealing with SYK model, which I will discuss, so then what you do is you do the thing that I mentioned, that you integrate out these C fermions and you generate this self energy, and then you do a Largen theory, which I discussed. You can again derive the Largen saddle point equations, which I will show. But in general, and then you solve the Largen saddle point, you get the Green's function, then you put in the Largen action, and that gives you the entanglement or entanglement entropy. Okay, but in general, if you are dealing with other approximations which are not saddle point approximations, there are such many approximations used in condensed matter like that. So then you have to actually calculate this path integral. Just calculating the Green's function is not enough. Okay. So then it poses a challenge in these calculations, which is even known for if you are trying to calculate, for example, free energy in Hubbard model using dynamical mean field theory. You have to do some kind of coupling constant integration to get it. So here it turns out that you can actually use the integrations over strength of this term. So the formulation I mentioned there, naturally the strength of this kick term is set to 1. But what you can do, you can actually just put a lambda here, just put a strength, so look into some problem. And then what you can show that this entanglement, so at lambda equal to 1, I will recover what I want. Lambda equal to 0 will give you decoupled, unentangled state. Okay, because lambda 0 doesn't couple this, the two replicas, right? So basically you can now do an integration, sort of an integration of this strength, and what you can show that essentially it is like doing kind of a work with this kick term, where you change the strength of the kick term and you do some work done going from 0 to 1, and this work done is just this expectation value of the kick term in the presence of some lambda, so it is only given by 2-point function. Okay, so basically you can get the, by doing this integration just through 2-point function, you can get entanglement entropy. Okay, of course you have to calculate the 2-point function in the presence of this arbitrary strength. Okay, so this is a general result. Okay, so this doesn't depend on any particular model. Okay, so this we have actually used in Hubbard model and all, which we are not going to discuss. So that's sort of a nice thing about this. So maybe even with the standard boundary also, you can probably do something like that. I don't know, but at least here it becomes very simple to do. Okay, like. Okay, so that's about this method. So I hope at least, so this is not directly related to SYK model, but I hope it is interesting to you. I mean, like, Okay. So now I am going to use this for the SYK model. Okay. And so here again the idea is that what you are asking, the general questions that you are asking when you are dealing with SYK type models and trying to calculate entanglement entropy is that, so what do you expect, what deviation do you expect? So I told you already that if you have gapless fermions, interacting fermions, gapless fermions in 1D like Luttinger liquid or free Fermi gas, non-interacting, you get this general result. Interaction doesn't have any effect on this result, okay, in one dimension. And in higher dimension, as I also said that there is no proof, but people believe that there is no effect, okay. This coefficient is also fixed by that same thing with some geometric factor. So this is for Fermi liquids. Okay, so the question you are asking that what happens to the non-Fermi liquids? So do you get a deviations from this? You still get this kind of L to the power d minus 1 log L or some completely different behavior? What about the coefficients? That the coefficient depend on interaction. Okay, so these are the questions that you want to ask here. So, this question has been of course asked for a long time, and there are people. I mean, there is no method to calculate it, but people have come up with interesting scaling arguments and all these things like Senthil's and other. And there are many works I am not mentioning, but that's sort of the interest. Okay, so to ask that if you have non-Fermi liquids, so what about the entanglement? And in particular, there are some non-Fermi liquids which are called these critical Fermi surfaces, which are which has Fermi surfaces but no quasi-particle, and there this kind of questions become even more interesting. Okay. Yeah. Quasi-particles. Yes. 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 Okay. So now let's. So rest of this will be quite simple actually. So I just remind you that this is what we discussed. The summary of what I discussed in the last two lectures. So you have the SYK model. And then in the SYK model, you have this non-Fermi liquid, which means that you have this divergent density of state 1 over square root of omega and a very strong self energy at omega going to 0. And this gives rise to this non-zero residual entropy in the limit like this. And that corresponds to this level spacing. Okay. So the question that we would like to ask that what happens to the subsystem Renyi entropy, in particular if you are trying to take the zero temperature limit, and the connection between, if there any connection between this residual entropy and entanglement entropy.
Residual is this S
naught. Yeah, S naught, yes. And another thing you want to contrast it with something which is not a non-Fermi liquid and which, as I also discussed, is very easy to get. Is just you put some hopping term and that will immediately destroy this non-Fermi liquid. Yes.
I unfortunately missed your second talk, but how do you define entanglement entropy in the SYK model?
Yeah, I'll discuss. Yes. Yeah, that's a good, important question. Yeah, you have to define that. Okay, so essentially if you put hopping, then it immediately destroys the non-Fermi liquid, but what you can do is you can still have a heavy Fermi liquid, which is the kind of thing seen in Kondo systems, where you have very huge electron effective mass, which is essentially translates to having a very small hopping compared to interaction. Okay, so even though it's a Fermi liquid, but still is extremely affected by interaction in terms of the effective mass of the particle, which gives you a very low Fermi temperature, okay, which is T square by J. And I also discussed this. Yes, sorry, yes.
If you take TH to go to 0, is it that of course as omega goes to 0, self energy goes like omega square, but when you go just a little above, it becomes the SYK form.
Yes, yes. This yeah, above the omega, above this, it will become SYK. Yes, yes,
So
yes. Yeah, right.
Thank you.
Yeah. Okay, so and there are some other things also you can use, but okay. So now let's come to Spencer's question. So how do you? So what is the meaning of defining entanglement here? Because anyway, it's a non-local, completely non-local system. So of course, because it's all connected, then you know that here these issues that I mentioned, that volume law versus area law, that will not really come. Everything will be volume law. Okay, so that's given. I mean, that's not going to change, but you can still ask how it changes with energy, temperature. I mean, things like that, with phases and things like that. So the way you define this entanglement is you still take the SYK model, which have a cartoon picture here, which has different sides, and you just choose some number of sites, NA number of sites out of total N sites. So there is nothing special about this NA number of sites when you are disorder averaging. So it just defines a fraction. Okay, so you are just asking that this fraction of system, how it is entangled with the rest of it. Okay, and is there any difference between Fermi liquid and non-Fermi liquid? So that's the way I am defining entanglement here, and it will be always volume law. Yes.
By volume law, you mean
yes, yeah, it will be proportional to NA or P. Okay, so we have been also doing calculations where you can do this calculation for pure state. So like KM type state, like so you can start with some pure state and you evolve it in imaginary time, and you prepare some low energy state. So those also can be done, but I'm not going to discuss that. This is some recent works that we are doing. But so in this work, I'm just going to discuss this particular protocol, which is you define a thermal density matrix rho e to the power minus beta h by z, and then you try to calculate this subsystem Rayleigh entropy, which at this stage of course is not entanglement because it has entropy, just thermal entropy into it, but then you try to take t going to 0 limit, and if you ask that whether you can get the ground state entanglement entropy, of course you can see that because I am going to take this limit, you will never be able to get ground state entanglement by this method, and that's what we will see. Yeah, you will see the S0 effect, exactly. Yeah. So okay, so now come back to your question. So there you have to do another replica here, which is this, you have to take this Rayleigh entropy and you have to then average over disorder. So there will be two replicas here. One replica you are going to take n going to 0, which is the disorder replica, and because we are calculating second Rayleigh entropy, then this will be just 2. I am not going to take any limit. Okay. Okay, so now again I am skipping this, but I believe me it's just a straightforward thing, derivation that I did is just a straightforward generalization of that. So remember, as I told you, that when you have this kick term, then all it is doing is that in the p fraction of site, it is giving these source fields, okay, and then 1 minus p, there is no source field. So my Bayer-Green's function essentially depend on the source field for the A subsystem sites. So you just put it in this G sigma field theory, and you just do the same thing that I did, and this is the large n saddle point equations that we will get. Okay, so the only difference in the large n saddle point equation is that earlier I got delta t tau plus sigma, which I got. Now I have sort of two parts. Okay, in this disorder average large n, 1 minus p for the B subsystem which doesn't have any kick, and then for the A subsystem which has this kick. Okay, and then the self energy expression has is same. I have just put a hopping here, so it's exactly same. Okay, so this is the kick term. So it's now of course, but the thing is that since this has a delta function, you can no longer solve it in the frequency that I mentioned. So you have to actually just discretize over time and then solve this problem, but that can be done. I mean, it's not that easy, difficult. You can do it for quite large discretization, at least this problem. It converges very fast actually. Yeah.
You solve it
Yeah.
numerically.
Yeah.
Data in the ultraviolet.
Yes. Okay, so let me just discuss the result. So first, to sort of check whether this method is working at all or not, right? I mean, so we just first check with something which you can calculate very accurately. So I take a model where I just have this random matrix model, which I discussed in the first lecture. Okay, so which is a non-interacting model. So I can take each disorder realization and I can diagonalize it, and for each realization I can calculate the entanglement entropy, and then I can average over disorder. So I don't need to use large n, I can directly do it using correlation matrix. Okay, and then I can do this large n thing that I mentioned in the last slide. So these are the two results. Okay, so you can see they are falling on top of each other. So these lines are the large n results, and these dots are the results obtained using, so this correlation matrix results, which is using the non-interacting diagonalization, and these circles are the results obtained using ED, the many body ED for this problem. And you can see that even for system sizes as small as n equal to 10 or something, they agree. So there seems like a very little finite size effect on entanglement entropy. Okay. In this, so I don't of course know why that is the case, but somehow the Schwarzian corrections are not important here, it seems. But yeah, I mean, this is of course non-interacting, but you will see the same thing in the SYK case. Okay, and here another thing is that of course this I am doing at some finite temperature. So if you are doing it at 0 temperature, so this curve should be symmetric, okay, because so this is the fraction of size whose entanglement I am looking into. Of course, it just depends on the smaller subsystem, okay, because that many degrees of freedom maximum you can entangle. And so at t equal to 0, this curve should be symmetric around p equal to 0.5. Of course, these curves are not symmetric because I am doing at finite temperature, and the reason they are not symmetric because you are getting entropy here, okay, because finite temperature entropy is coming here. So if you go on taking t going to 0, which is shown by taking these points and trying to extrapolate, as you can see, it extrapolates nicely to 0. Okay, so that's what you should expect, that t going to 0, you should get back the entanglement entropy.
The p scaling.
I'm coming to that. Yeah. Okay. Yeah. So there is a universal scaling for with p at small p. So that's the result. So now let's look at SYK. What happens? Okay. And as we expected, so let me just take you through it a bit slowly. So again, the lines here, these lines are the large n calculations. And this thing is actually a exact diagonalization calculations as far as I remember. So okay, so again, I mean, all the curves I don't remember exactly, but so basically in the SYK case, what you will find, so let me show this plot. So SYK case, again, you find that first of all, this asymmetry around 0.5 is much larger at that temperature, okay. And in fact, there is a very large value at p equal to 1 where it should have gone to 0 at low temperature. It never almost goes to 0. Okay, it never goes to 0, not almost. And you can take this value and you can try to extrapolate. And if you extrapolate, you will get exactly that residual entropy. Okay, and you can analytically show that it is extrapolating to the residual entropy. No, small temperature also it is mixed, right? So typically you would expect that when you go to lower and lower temperature, it will purify. Because of the yes, yeah, it is still mixed. Yes, it is not maximally mixed because it's still less than sort of log 2 value, right? It's like some value 0.46 or something. So it's the ground state has less entropy than the infinite temperature, which is log 2. Yes. Yeah.
That's what I was going to say.
Right.
In that subspace.
Yes. No, here I am not calculating von Neumann anywhere. Oh, okay, so that you can show, yeah, I mean, we have calculated the Renyi entropy also. It gives same results, I think. Yeah, this is for the Renyi, yeah, this value I think doesn't change as far as I remember. No, okay. So the large n calculation disorder average saddle, the numerical calculations average over many realizations. And again here the same thing. So of course for the SYK case, as you can see that there is a large finite n correction, meaning if I do exact diagonalization then it goes to 0, right? And the SYK never goes to 0. So of course there is a very large n corrections which is trivial in this large n theory, in the sense that you don't expect to get back this entanglement. So what you can do, and this is sort of a very striking result. Okay, I'll show that, but let me come to what Sandip was asking. So you can, in fact, yeah, sorry, yeah. I see. We didn't really study it because this model there's only one scale, right? So there is. Oh, in the numerical calculation, you mean? That we didn't check. Sorry. Yeah. Numeric. The large n calculation because okay, I mean there is only one scale. I mean, right? So it should not. I mean, I can just scale it, right? I mean.
Even numerically,
yeah,
you just when you say
numerically also you can scale the full Hamiltonian by j, right?
No, I mean as a function of beta times j.
Oh, beta j, right. Oh, beta j. So that is the beta j dependence, right? Because I have taken j equal to 1. Yeah, right. Okay, so now actually you can using this method. I mean, I think you can show it in other methods also. But I mean, you can essentially show that there is an analytical result you can obtain p going to 0. Okay, so which is for the complex SYK is given by this expression. Okay, minus p log 1 minus n whole square n, where n is the occupation. No, not np. This is the occupation of the complex SYK. So at half filling this will be 0.5, and half filling this will be maximally entangled. So it will be log 2. So if you take a small subsystem at half filling that is maximally entangled, so the rest of the system always acts like a infinite temperature bath to that system. Okay. So it basically varies like log to p. If you see this slope, and this p is just the fraction of the subsystem. So yeah. So I mean it should vary as p. That's not a surprise. I mean the fact that it's log 2. Yeah. Yes. Yeah.
How do you do this analytically? You solve the G sigma?
Yeah, I mean it's like basically if p is small, the subsystem is much smaller. You expand in p basically. Yeah. Yeah. Right. Yeah. Yeah.
Similar.
Yeah. Okay. Oh, okay. Yeah, so now what you can see that if you put a hopping term, it immediately changes the result completely, even a small hopping term. Okay. So in fact, if you put, I just now put this J and this small hopping term, which will make it a heavy Fermi, and you can see immediately I don't get any residual entropy. Right? It approaches quite nicely both in large N and ED, almost this zero value. Okay, almost recovers in time. So you can see that there is a huge difference between this SYK low temperature and even a small TH, which is even seen in entanglement. And you can look at this as a function of this hopping basically going from heavy Fermi liquid to the SYK limit. You can see all these things. Okay, so this I will probably skip. This is not, yeah, I think not that important. Okay, so this is let me come to the another part of this. Then I'll stop and then I'll go into some quench thing. Yeah. So now one thing you can do. So originally, of course, I asked these questions about the scaling that L to the power d minus 1 log L. Right now, the model I took there, you cannot really ask this question. As Spenta answered to Spenta's question, as I answered that you always have a volume law. There is nothing that you can distinguish apart from this residual entropy coming in and all. So now what you can try to do is that you can try to create some kind of space, right, which is very well known in the SYK model, which is you take many SYK dots and then you put it on a lattice. Okay. So now once you put it on a lattice, then of course, and then you define some local interactions between these dots. So dots are completely all to all. There is no locality in the dots, but these quantum dots, if you put on a lattice and then you define some nearest neighbor interactions or hopping, then you will get a locality, at least artificial, okay, in this model. So then you can ask what is the scaling of entanglement with subsystem size now in space, okay, not this subsystem. So this kind of thing has been even just after this SYK thing came to all the discussion, people immediately generalized this type of did some generalization, and again in the condensed matter context, that the reason this was interesting is what you are going to do, you are taking this non-Fermi liquid quantum dots and you are putting on a lattice. So what happens is that at least in this simplest version, the saddle point, the large N saddle point of this model doesn't change when you go from the dot to the lattice. It's just some renormalization of the coupling. However, you can still generate non-trivial transport, and so it can help you to understand transport in in systems without any quasi-particles. Okay, so for example, whether you get diffusion, what kind of temperature dependence you get, and all these things. Right, so that's why this is also interesting from the condensed matter perspective. This kind of generalization, and so now you can ask that if you have this system and then I try to calculate the entanglement entropy of this subsystem using the method that I discussed. So again you can do it quite easily using this method. So what we again do some benchmark, meaning we take essentially some non-interacting quantum dots with 10 sites and then put them on a lattice and then use these two methods, the large N methods and just the direct diagonalization and this, and you can see that they agree like perfectly well. This large N results and fixed disorder results and then with disorder average. Okay, so everything large N seems to work very well. I mean even for N equal to 10.
Why does it work so well?
I don't know.
Because it's all to all. So
probably, yeah. Yeah, right, yeah. Okay, so you can do it now for the interacting case where you put interaction in the dots. Okay, it turned out that this result, I mean, in retrospect, we found that it's not very interesting, and you should not actually expect to get this type of physics that I mentioned, that is log L and L to the power d minus 1. So what happens is that if you, so this is what I'm showing here. So what I'm showing here is the entanglement entropy of this subsystem whose size I am varying. Okay. So what I told you earlier, so this is in one dimension. So what I told you earlier, it should go like log L. I mean, if you have some kind of a Fermi liquid and things like that. But what you find instead here that you both for the interacting and the non-interacting chains like that it initially increases. So it seems to have some increase, which okay, you have a very small range, you can probably fit with log L or something, but then eventually it saturates. Okay, it doesn't grow, continue to grow. I mean, the system size is much larger, so it saturates. And this is actually not, I mean, it was somewhat understood. So because this system, what is happening is like a completely disordered system. It doesn't have any Fermi surface. Okay, because I'm putting some random hopping between these dots. Okay, so there is no, so without even if I don't put the SYK interaction, there is no dispersion in the system. Okay, it's a completely incoherent diffusive metal. Okay, and so there should not be any sharp Fermi surface in this material. Okay, because it's just a completely diffuse. There is no dispersion to define a Fermi surface here. And for this kind of system, actually, it is known from some arguments that what you should get is some kind of C effective, which is nothing to do with the central charge or anything. It's just some coefficient, some log behavior, which is cut off at some scale, and this scale is basically mean free path of the diffusive metal. Okay, so this is known from some arguments earlier by Andrew Potter and others.
So there is a well-defined notion of a mean free path in this case, is it?
Yeah, it's not very clear, but you can still sort of, yeah, so mean free path here again, I mean, okay, so I should say for this particular model, there is no clear well-defined notion, so you are right. So the Potter and all considered some model where there is a sense of mean free path. Here, this is just some length scale that is emerging, which is just coming from the entanglement, which is just cutting off the entanglement. Okay. So this is not very interesting in that aspect. So if you really want to ask this question with some work that we have been doing, you have to really take this kind of models which has some energy dispersion. Okay. And then do it. So we are doing some calculations for some critical Fermi surfaces, which can also be modeled with some version of SYK, which is this Yukawa SYK type models, which I am not going to discuss.
So this says that as far as entanglement is concerned, it's like a gap. I mean, it's
yes.
with a kind of
Yeah,
gap,
right. Yeah, it's some non-unit. So you can see that it depends on interaction. So for example, interacting chain is some value, okay, and this for non-interacting is some value. Okay, in fact, I mean, if the C effective also changes with, I mean, whatever you, I mean, there is nothing special about this, just some fitting parameter coefficient. It changes with interaction. I mean, I don't have any interpretation of this really. Yeah.
So in your way of calculating entanglement entropy, you had this kick term, right? Can you maybe comment on how that changes with these different models?
The kick term doesn't change, so it's same.
Then
yeah.
I thought that is the thing that then what?
No, the Hamiltonian changes, right? Because I had essentially the action. So kick term is same. I mean, you can. That's what I said. You can use it for any model, right? So that formulation doesn't change. So it's just the Hamiltonian input that changes all these results, right? So yeah, I mean, of course, kick term changes if you take different entanglement cut, different kinds of setup, right? So which you can take two disjoint subsystem, you can take full contiguous subsystem. I mean, that the kick term changes on that, the geometry of the subsystem that you check. Okay, so I'll yeah. So here I'll maybe.
Sorry, this is really interesting. So the dependence of L naught on J is two scales here.
Yes.
That ratio.
Right.
That's something you could probably.
Yeah, we actually had a plot. I think I'm now some time ago, so I've forgotten. So we did try to study this, but not very seriously because we are sort of. Yeah, I mean, we thought we are not getting anything interesting, so we didn't study that much. But okay, so I'll just briefly mention some work on thermalization, but very briefly because I already started a long presentation. But before that, any question on these things? Yeah. Okay, so let me just, and I don't want to extend it till maybe the full time. I hope that is okay. I'll just, because too much information, I guess. So I'll just discuss some example of looking into this question of thermalization in the SYK model. And again, the methods are some generalization of the same G sigma action that I wrote to Schwinger-Keldysh formalism. Okay, so it's just, so again, you saw the derivation here. So you just generalize it to the Schwinger-Keldysh thing, you will get the same type of equations, okay, or written on the Schwinger-Keldysh action. So that's, so it's nothing really technically here, anything different apart from applying to Schwinger-Keldysh, the basic method. Okay, so I'll just discuss sort of the main some results, but I mean these results are just to demonstrate some principles. I hope not to sort of specific results. Okay, so and I'll the question I'm going to ask is that I mean the originally as I started saying that can you distinguish Fermi and non-Fermi liquids using thermalization rate? Now, one thing we saw, I mean, I didn't really discuss it in detail, but the Lyapunov exponents could distinguish them. Here what I'm going to do is just look at the full non-equilibrium evolution and trying to see what happens. And for this, I'm just taking this model, I mean, because this model that I discussed, which is just a generalization of the SYK model, where you have the SYK fermions, and then you have this extra set of fermions. Which you can call from this graphing plate example, you can call them lead fermions, okay, because they are just coming from these leads that you attach to this graphene quantum dot. So, so I'm just taking this model because this gives you a lot of flexibility to do different kinds of non-equilibrium protocol. You can go from Fermi liquid to Fermi liquid quench, and then so there should be NFL here. So non-Fermi liquid to Fermi liquid, and then you can do quench in Fermi liquid. You can go across this quantum critical points. You can do a lot of different things with this. Okay, and then another question is that you have here this non-zero entropy in this site. So even if you start at 0 temperature in the large N theory, you have this entropy, and if you quench to the Fermi liquid, what happens to the entropy? So how does it manifest itself? Okay, so that's those kind of questions you can ask here.
Sorry to interrupt. Sumilan, you have mentioned it, but if you just had your quadratic hopping term and not the 4 Fermi, how does the OTOC grow? It doesn't saturate? I mean, there's no chaos actually. Sorry.
No. So if you just have this, if you just have this, there is nothing. Chaos. But if you have both of this, then T square lambda L goes like T square. No, if you have a Fermi liquid, then lambda L goes like T square rather than 2 pi T. Yeah, okay, that's what you were asking. Yeah, for non-interacting model, there is no growth. Right. Okay, so the quench that I'm going to do is maybe not very physical quench, but what you are, okay, maybe it's okay. So what we are just going to do, we are start with these two decoupled systems like this SYK and this lead fermions. So initially they are decoupled, and then at t equal to 0, I switch on their coupling. Okay, and then I can switch on the coupling depending on this m by n ratio, which is this. So remember, let me remind you, there is a quantum critical point here from a non-Fermi liquid to Fermi liquid, which goes through p equal to 1. Okay, so I can. So this p is not the p that I was mentioning. So this p is this ratio of m by n in this model, not the p of the entanglement. So you can actually just quench this system such that it either ends up in a non-Fermi liquid or end up in a Fermi liquid or end up at the critical point. Okay, you can do the quench like that. And what we are going to start with, we are going to start with a state which is a SYK non-Fermi liquid, a product state with a Fermi liquid of this non-interacting gas. And then I am just switching on these things. So very similar, I think, in a much more sophisticated setup and questions I think Spenta and Gautam has also worked on. And they have looked into beyond large chain. I mean, and there could be some relation between that, but I can't really, I don't know that much, but yeah, I mean, somewhat similar. So basically, you have some kind of a bath, and then you have SYK, and then you initially start with this decoupled thing, and then you quench. Okay, you switch on this thing. So you can do a sudden quench and you can do a slow quench. And so what you expect here is that, so this lit fermions actually gives another advantage, because this lit fermions originally has some kind of a density of state. So it has some single particle levels, okay, which I am denoting with epsilon, because so let's say if you are just doing diagonalization, then if you diagonalize this, you will get some epsilon single particle level. So I can actually just try to ask that what is the occupation of that level, okay, what is the occupation number. So that you can ask here. And what you expect, so if you are in a Fermi liquid, so then according to Landau ideas that a Fermi liquid, so if you are do adiabatic evolution, then the Fermi gas will evolve to Fermi liquid, okay, under this evolution, if I do it slowly. So if there is no phase transition, no level crossing, then you expect it to go to a Fermi liquid smoothly from a Fermi gas. And then if you look at a quasi-particle state, then the quasi-particles will be dressed. So original non-interacting electrons will be dressed, and it will give you a quasi-particle. And what it will still have, it will still have a discontinuity of their occupation at the Fermi surface, which basically tells you that there is a well-defined Fermi surface and it's a well-defined Fermi liquid. Okay, so even in the interacting case, this T equal to 0. So this is valid only at T equal to 0. At T equal to 0, rather than having this full jump of 1, you will have some finite jump, but that will still tell you that it is a Fermi liquid. So you can track these kind of things in this problem that I am going to discuss. Okay, so this is the way you can trying to see how a Fermi liquid evolves to a non-Fermi liquid or non-Fermi liquid to a Fermi liquid. And for a non-Fermi liquid, you expect that there will be no, even at very low zero temperature, there will be no jump. So there, yeah, you can ask this question. I think I already told you about some of these questions. So one thing I'm going to ask, maybe it's not a very valid question at large n, I'm not completely sure, but so how does it evolve from a non-Fermi liquid to a Fermi liquid if you do it very slowly? Can you adiabatically go from a non-Fermi liquid to a Fermi liquid? Yes. No, here there is no Fermi surface, because still I have a single particle level. So I am not defining in terms of a Fermi surface, but still, since I have a well-defined single particle non-interacting levels, I still can define occupation of those, right? Actually, it doesn't depend on whether you have a Fermi surface or not. As long as these are non-interacting, it will still have a Fermi statistics. Okay, if you have just a so like even this random matrix model, right? So if you take the random matrix model, yeah, it doesn't really require Fermi surface. This jump will be there. So if you have just this part, right? So then I can just diagonalize, and then at ground state, because I can only occupy up to something, and then there will be a jump, right? So the occupations will be still this jump of 1. Okay. So what I am going to, so there is no Fermi surface, but still there is a jump.
Because there is this Erdmenger theorem, so which holds.
So Erdmenger theorem you cannot directly apply here, because I mean there are some works trying to do that also, but yeah, so there is no, I mean you cannot define a K, I mean there is no K space volume or anything like that here. Okay. So there, yeah, so there is no no analog of Erdmenger theorem here, but there is still a jump. Yes, green. I'll show the definition. Yeah. Okay, I want to quickly close this thing. So yeah, so these are the questions, and particular, as I said, I want to see sort of what happens to this residual entropy, how it manifests itself, at least in the large n. So yeah, so the you formulate in the Swinger-Keldysh path integral. So the same G sigma action now you write on this contour. Okay, and you can write down the same set of same looking large n equations. Only thing is you have to now define this plus and minus. So there will be Green's functions which are between plus plus, minus minus, plus minus, and minus plus. It turns out there are only 2 independent one that you have to track. Okay, so yeah, you can, so some numerical detail you can do. This I already said. So okay, so let me just quickly just mention 2 results, and I'll finish actually. So okay, so now coming back to this question that how do I define this this Z? So what you can do, you let's say start with the non-interacting model, right? So at T equal to 0, when I have not done quench, then I have a Fermi gas and I have a SYK, which are decoupled. So at T equal to 0, you can look at, so you can imagine that I just do a I have a spectrum, the non-interacting spectrum for this model, which is denoted by some epsilon. It doesn't have any well-defined k or anything, but still there is a well-defined energy. Okay, there will be delta function peak at those energies. So there is an energy, and given that I can write down the Green's function at that energy of this, which is, and the occupation is given by like a time dependent occupation you can obtain from this equal time Green's function. Okay, G less essentially. And then if you look at so my Fermi the chemical potential is at mu equal to 0. So if you look at this quantity 0 plus and 0 minus, that difference essentially gives you this jump. Okay, because if I take epsilon, this n psi epsilon here, 0 minus which is here and 0 plus which is here, this difference is giving you the quasi-particle residue. Okay, so this is how you try to track. So at t equal to 0, at 0, so this t is again, no, sorry, bad notation. So this t is not hopping, this is time. Okay, so at t equal to 0, I have this jump. I am going to ask how this jump evolves. Okay, as I change that, as I evolve. So what you find is this result, that if you are in the non-Fermi liquid state, then this initial, so this jump of course has to go to 0. Okay, so it oscillates and then goes to 0. So this is, if you am quenching this system, so I have this two system, I choose a P so that I end up in the non-Fermi liquid phase of that phase diagram. Okay, so let me show you what I mean so that you are not completely lost. So I'm starting with a SYK non-Fermi liquid and some Fermi liquid, and then at time t equal to 0 I am coupling them, and I am taking a parameter P such that at the long time they will end up here. Okay, if they thermalize. So that I am quenching to a non-Fermi liquid of this combined system. If I take a large P, then I should end up at large time I should have end up at the Fermi liquid. Okay, and then I am going to see the distinction. So what you see is that there are very different ways they relaxes in a non-Fermi liquid and a Fermi liquid. So Fermi liquid, it relaxes very fast, but there are some oscillation. Non-Fermi liquid relaxes very fast, but there are some oscillations. Whereas in the Fermi liquid state, they actually relax through pre-thermalized states. So there are plateaus which are called pre-thermalized plateaus. So it looks like they have thermalized to some value, then again decay, and then again stay and again decay. Okay, so this is what you get, and this is actually something similar also seen in Hubbard model. I mean, this is not very special to SYK model. When you quench from a strongly correlated metal to a weakly correlated or you see this kind of effect. Another thing you can try to look at is whether this system has thermalized using the KMS conditions or in fluctuation dissipation theory. Okay, so you can look at this ratio of two types of Green's functions, and that if you thermalize should become the Fermi function at the expected temperature for the final state, because you have done some quench, you know how much work that you have done, and you know what will be the final temperature. Given that you have an expectation of a Fermi function, you can see how close I get to this Fermi function. Okay, so and what you find that again non-Fermi liquid relaxes very fast. So this is sort of some relaxation of some part of the energy which is not conserved, some part of the Hamiltonian which relaxes, and this points here indicates what should be the expected thermal value, and as you can see that they relax very fast. Whereas in the Fermi liquid, they seems to take here, for example, at deep in the Fermi liquid, it seems they will take much longer to relax. So another interesting thing is in this pre-thermalized state, you see that these fermions has not regained the Fermi function. So it's sort of a non-equilibrium distributions that they keep. Okay, so this type of thing. Okay, yeah, you can do few things. So let's end with. Let me end with this last thing. So which is again, as I said, I'm not very sure. It's a meaningful question. Maybe you can, if people can tell me. What I'm going to ask here is that I'm going to do a very slow quench now. So I was doing a sharp quench, so I was changing the Hamiltonian suddenly. But let's say I now switch this thing slowly. So I basically change P very slowly. Okay, sorry, the coupling constant very slowly. Yeah. So then initially I had this, so let's say initially I was 0 temperature for both the Fermi gas and the SYK, but I had some finite entropy. at T equal to 0. Now, of course, at long time, I cannot really thermalize. If I go to a Fermi liquid state, I cannot really stay. Even if I do it adiabatically, I cannot really stay in the ground state because I have to budget for this entropy, right? That was there initially. So even if I do it very slowly, it will never be able to stay in the ground state of the Fermi liquid. That's the expectation. And then so basically this should say that it should violate adiabaticity. Okay, you can't do it. You can never do it slow enough so that you stay in the Fermi liquid ground state, and you can
You can't because in the Fermi liquid ground state there is no gap, right?
you can't because Fermi liquid doesn't have this entropy. So initially there was this entropy. So where would the entropy go, right? So it should create some excitations. Right, if it manifests. So, so you can look into this quantity. So you can look into the expectation value of the final Hamiltonian in the initial temperature. So if it doesn't heat up, if the system stays in the initial temperature, then whatever instantaneous energy after quench I get should be same as this, if I can do it adiabatically. Okay, of course it will depend on tau. So at finite tau it will always be finite, but I can try to take tau going to infinity and ask that do I recover adiabaticity. So what we find that at least to the extent we could study, it seems like it actually seems to recover adiabaticity. Okay, meaning this energy seems to follow a power law which goes like tau to the power some eta p, which depends on p, and eta p is less than 1. So if you try to extrapolate it, it will seem that this entropy will not manifest. Okay, which of course I don't believe this result. I mean, it must be that at very large time this entropy will come and then manifest it as excitations. But at least if you try to follow the early trend of as a function of tau, the time over which you are doing this quench, it seems that the entropy is not manifesting.
Sorry to ask you this, but the fact that you have so many e to the minus n space levels, doesn't it mean you cannot be adiabatic?
Yeah, that's what I'm saying. You cannot be. No, but what I'm saying, surprisingly, this violation of adiabaticity seems to be happening much longer time than we can study. Okay, so it's that was just the simple idea. Okay. Okay. Anyway, so that's basically it. I mean, I wanted to just discuss this. I'll just stop here. And thanks for your attention. Yeah.
Since you have such impressive results for entanglement, which are hard to normally obtain, the OTOCs are, of course, notoriously hard to compute analytically or even numerically.
Yes.
But
Entanglement.
the OTOCs in some system like SYK.
Yeah.
Because you have to extrapolate to large n.
Right.
But do you have some?
Yeah, so I think maybe the Schwarzian way one can do, because essentially this kick term creates a non-zero action for this Schwarzian. So you can still use the conformal solution and then probably use the Schwarzian. So that will be easier to sort of solve, because it is just not a bilocal field. It's a field which depends on a single time. So those equations may be easier to solve. That's my case. Because this kick term violates it generates a non-zero action for the Schwarzian. Yeah.
So sorry, just then let me back up. Are the entanglement calculations results you showed, let's say I'm at a low enough temperature, phrasable in terms of a Schwarzian coupled to kick term
I think so, yes. I mean, so I have to still use the non-kick conformal solution, which will give some initial contribution. Of course, this method I did only large n. I didn't take any finite n, but Schwarzian will contribute even in large n, right, in the non-conformal corrections.
Yeah.
So that thing one may be able to get.
Okay. Yeah. So that would be kind of an analytic.
Right, analytical.
Okay, thank you.
Yeah. Not yet, as far as I know. I mean, Rajdeep has used it for some bosonic systems. But as far as I know, he has not used it for Bose-Einstein condensation.
Yeah, I have one question. So,
Sure.
From the last few years, people have been talking about spin glasses and SYK models. They have some similarity. Can you comment on that?
Comment on that.
Comments on that?
Yeah, so actually we have also done some work to try to find these relations between spin glasses and all, the chaos in spin glasses, which I didn't mention. So there, you are right, there are very similar things there. Yeah, so it turns out that the spin glasses, at least the spin glasses that people have looked into, so we have looked into this SY spin glass, the Sazdev, the original parent model of this. And then also some other well-known spin glasses which are called quantum P spin glasses. So you can do this kind of large N theories and calculate OTOC there. Of course, one interesting aspect there is that in spin glasses, when you calculate OTOC or anything, you have to include this replica symmetry breaking. So that essentially makes this calculation interesting, how the replica symmetry breaking actually changes the OTOC or the Lyapunov exponent. Okay, so those kind of interesting things are there, but all these things are far away from this maximal chaos. And also in spin glasses, for some reason which is slightly technical, the thermodynamic solutions will not allow you this conformal. So although the equations, you can still have conformal solutions if you just look at the structure of the equation, similar type of argument like SYK. But it turns out if you try to do them self-consistently, there are some constraint, which is like this chemical potential constraint. But there also there is some constraint, which is the value of spin essentially. Okay, so it turns out those constraints doesn't allow these conformal solutions. Okay, if you do it self-consistently. However, I think Felix Hahel and other people, they have essentially tried to say that in some non-equilibrium situations, you might have this conformal. If you create some non-thermal distributions, you can have this kind of conformal solution, even in spin glasses.
No more questions. We can thank Sumilan again.
Thank you.